So far this semester, what we've built are effectively the rules. So how we can interact or bring different molecules together and what they can produce. So really what chemistry is giving us is a rule set. You've already seen rule sets in your life. Math, physics, and general life allows you to come up with different ways to relate different units. So when we're moving into chemistry, well, chemistry is giving us the instructions on how to build things. Okay, so we look at formulas. Well, a formula gives us the atoms used to build a molecule. Equations give us information on how molecules can then build new molecules. So that's just basic instructions on what we work with. Okay? And just like in math or physics or life, when we move to a slightly different environment, we invent a new system or a new measurement to allow us to quantify what we're looking at. And so because chem is so tiny, we need to invent new units as well. And that new unit that we end up using in chemistry is defined, or is the mole, okay, which is this big kind of nebulous concept that everybody freaks out about. But really it's just a new unit that allows us to shrink things down, or the sheer scale of things, kind of actually up. Because if we look at atoms, they're so tiny that we need to scale them up to a scale that we can work with. Okay? So let's take a look at some examples. Okay, if we've got this picture, we've got Lego Winterfell. And we might say, okay, well, how many Lego bricks went into this? So I can be a jerk and ask a quiz question and see if you get it right. And the actual answer is somewhere on the order of 4 with 5 zeros after it. That's the number of bricks that went into this. That's a lot of bricks. And so what we'll ask is a simpler question. How might we say that without all those zeros? Okay, so hopefully what you came up with was something along these lines. That we have 400,000 bricks. So what we're doing is, or brinks, because you know brinks makes sense. What we're trying to do with this English is trying to take the sheer and utter scale of 400,000, because that is so large that our brain starts to have a hard time comprehending it, that we convert or build a new unit, okay, or a new measurement system. And that measurement system here is 100,000. Okay? That gives us some context of where, decimal place-wise, that 4 should be located. So it's just an idea of a way to approach and kind of think about and adjust our scale. And so the mole is really doing the same thing. Okay, so let's look at another example. If we say a farmer has 72 chickens and each chicken lays 2 eggs a day, how many eggs can the farmer collect per day? Okay, so because we're early on in this, we'll walk through this one together. Okay, as we start with all problems, we want to write down what we want as an answer. Okay, well, we want eggs per day as our unit. Okay, well, if we go through and say, well, what do we start with? Okay, I have a conversion here that says 2 eggs per day, so I'm going to start with that. I can get 2 eggs in 1 day. So I'm converting the English into a mathematical expression. Okay, well, but a chicken can go through and produce, yeah, we're going to run with it anyway. I'm not even going to rewrite this. We get 2 eggs per day from 1 chicken. So we actually have to expand that out. Okay. Well, as an interesting feature, that doesn't quite get us to our final answer. We just wanted eggs per day. I have 72 chickens, so I can drop in that value into my conversion. What happens, the units of chickens cancel, and I would then have my answer. So all I have to do is then multiply that out, and I would have 2 times 72, and I get a whopping 144 eggs per day. Okay, and because I told you I don't like that unit, let's write it like that. Eggs in 1 day. Okay, we might say, well, cool, Mike, that wasn't that hard of a question to solve. Okay, but let's add a little bit of a wrinkle to this. What if the farmer can't comprehend numbers larger than 20? Okay, so what do I mean? Well, we just went through and solved that we can tell the farmer that he gets 144 eggs in one day. Well, but he doesn't understand numbers larger than 20. And that means when we say 144 eggs, he's like, I don't know what that means. You voodoo magic at me. Okay? So how can we then adjust this representation so that we can better explain to the farmer how many eggs he can potentially get? Okay? That's an interesting dilemma. Well, we might have to think of other systems that could allow us to do this. And hopefully one of those other systems that you can think about is that when you go into the store, you don't buy X number of eggs, you buy a dozen eggs. Oh, okay. So I know that 12 eggs is equal to 1 dozen eggs. So when I do this extra calculation, I end up finding out that we get 12 dozen eggs per day. Okay, so now when we go back to the farmer, we can say, well, you may not understand 144 eggs, but if I take these 12 out and set them in this crate here, okay, you get those 12 eggs, but now you get 12 sets of those. Okay. This now changes his perspective on it, and now he can wrap his mind around what's going on with it. And while this may seem like a silly example, that is exactly what a mole is doing. Except the issue with a mole is that that number is a lot larger. Okay? So we're trying to come up with a new unit system as a way to count things that allows us to represent. Okay? So let's go back to our chemistry. Okay? Our formula provides a recipe to build a molecule. So let's say we were going to look at, I forget what the quiz question is, so we'll see, sodium carbonate. Okay? I want to know how many sodium atoms I need to build sodium carbonate. Okay? And for those of you just that need the practice with nomenclature, let's go ahead and write that out. I'm asking for sodium carbonate. Okay? Our follow-up question will be looking at the equation. The equation provides us a recipe that allows us to build new molecules. So if I take, say, a whole bunch of sodium carbonate and a whole bunch of water, and then one molecule, that says molecule, trust me, of CO2, how many molecules of sodium hydrogen carbonate can I make? Okay. Well, that's what our equation should help us figure out. Okay. So that then addresses kind of the next part of this, is we now need to go into the lab and use this recipe, okay, to measure out our reactants so that we can mix and then make our sodium hydrogen carbonate. So that's the whole point. We've got directions now, we just have to follow those directions. Well, how do we measure our reactants? That's an interesting question. Okay, well, we would typically measure using mass. So where might we find information about our mass? Okay, well, our periodic table has some information about the atomic mass. So if I was going to determine the mass of sodium carbonate to measure out my first reactant, I then need to determine out its atomic mass. And we can use our periodic table, and we've got atomic numbers and atomic mass. The atomic number, if you remember correctly, is the number of protons, okay, which do contribute to mass, but our atomic mass needs to account for all particles that have mass. That's really going to be the number of protons plus the number of neutrons. Okay, so we need that information. So if I was going to figure out the mass of sodium hydrogen carbonate, I could use the periodic table and look up the mass of a sodium atom. Well, the sodium atom, according to our table, is 22.99. Okay, and our unit was our atomic mass unit, the mass of our atoms. Okay, we could look up carbon, and carbon is our 12.01 atomic mass units. And we could also look up our oxygen, and our oxygen comes out at 16.00 AMUs. And if we combined all this information together with perhaps the last piece of information, our formula, we could determine the mass of the sodium hydrogen carbonate. So if we go back to our question now, okay, we need to go into the lab and we need to measure out 105.99 AMUs of sodium carbonate. Okay, that's assuming I did the calculation right, which hopefully I did. Okay, so I go into the lab and I go to my balance that measures mass and I say, magic balance, tell me the mass of this. Okay, and the unit it's going to spit out will be what? Crap. It spits out grams. Well, I measured this in AMUs, so I'm going to need a conversion factor to get from AMUs into grams. Okay, so just like we've done before, go through and solve for the mass in grams of sodium hydrogen carbonate. Okay, so our one molecule, so we can get a feel for this. And I was just going to use the magic of time to fix this for us, but let's go ahead and actually write it out. We write down with what we start, or what we want at the end. We want grams. Okay, and where do we start? Well, I'm trying to get to grams, so I'm actually going to start with 1.661 times 10 to the minus 24th, and I'm going to put that in the numerator, because that's associated with my grams. And unfortunately, that also then brings in AMUs. Well, I don't want AMUs in my answer, so I need to cancel those AMUs out with something. Okay, so this is now relevant back to the question I'm looking at. I know that I have 105.99 AMUs for my sodium hydrogen carbonate. That's going to be over 1. If we check my units cancel. And I now have a magic answer for this. And unfortunately, when I looked at that magic answer, this number is going to be kind of tiny. Okay, it's going to be so tiny that it's not actually going to measure on my balance. Our balances are kind of nice, and our balances will measure down to 10 to the minus 4. So we're only off by 20 orders of magnitude. So something's gotta change here. Okay, we can't measure a mass that small. So we've got a bit of a problem here. Okay, and this is where Avogadro's number comes into play. Avogadro noted this issue. Okay, he said, well, if things are too small, we can't measure them in the lab, we're going to have to come up with some system for this. So when the value was later accurately quantified, we gave or assigned his name to it as Avogadro's number. And so what we decided to call it was a mole. As an instructor, I prefer MOL as opposed to MOLE. I don't know why, that's just the way I grew up with it, so be aware of that. And we've defined that to be 6.022 times 10 to the 23rd atoms. Okay, this is just a conversion factor, much the same as 1 dozen was equal to 12 things, okay, or objects. Okay, not 1 dozen equals 12 grams, okay, unless we're counting each of the gram pieces. Okay, it's not a mass; it's a thing. Okay, it's not a description; it's a thing. Okay, so really, all this does is give us a conversion factor. Okay, well, let's see what we can do with this conversion factor. What happens if we start with 1 mole of carbon atoms? Okay, I want to know what the mass is, and what a bad question because I didn't specify the unit, but I want to know the mass in grams for 1 mole of carbon atoms. Okay, so this time I'm going to let you run at it all you want, and we will use the magic of time. So please go through and solve that. So hopefully you've got work that looks very similar to what's shown down here. In theory, you should have everything easily in red, but you might have missed the things in purple. Okay, so let's take a closer look at those. You'll notice that when I wrote out 12.01 AMUs, I didn't actually, or I haven't in the past, defined that this is looking at 1 atom. But that is by definition what it is. An AMU is an atomic mass unit, which then means I'm looking at a single atom. That's why it's atomic mass unit. Okay? When I add that unit in, that helps me incorporate Avogadro's number in the next calculation. That I know 6.022 times 10 to the 23rd atoms of carbon are 1 mole of carbon, and so I can set up that conversion. And then I can bring in the 1 mole of carbon that I was given at the very beginning. Okay? You might have missed or forgotten our gram to AMU conversion, but that was just up on the slides. Okay? And if we go through and punch this all into our calculator, we might go, oh God, Mike, don't make me do this. That is way too much work. And if I do the math real quickly, divide by 4, subtract the 3, I should end up with 12.01 grams of carbon. Well, wait a second. Isn't 12.01 grams of carbon the exact same thing that was written on the periodic table in AMUs, except now it's in grams? Well, what happened? Okay, this is the power of the mole. Okay, this is the power of Avogadro's number. It allows us to scale up such an incredibly tiny mass, okay, by saying we're now looking at an incredibly large amount of those tiny masses, which then means the number that we see on the periodic table for our atomic mass is also the mass for 1 mole of our species. That's pretty incredibly cool. Okay, so the real power behind Avogadro's number means that when we look at the periodic table and we look at atomic mass, it is no longer atomic mass. Because atomic mass, quite frankly, is a completely and utterly useless unit because we won't work at the atomic scale. Okay? There are a few of you that may get there, but most of us won't even get close to that. Okay? Which means, really what we're looking at on the periodic table is the molar mass. Well, our unit for mass was grams. Our unit in reference to molar is moles. We're looking at the grams per mole for an individual substance. This is incredibly powerful, and it shortcuts a massive amount of calculations. Okay? So this is the big deal of Avogadro's number, that we can look at the periodic table and get a mass to mole ratio. That mass to mole ratio is what's going to drive nearly all of our calculations through this semester and the next and the next and the next and the next and probably the next then as well. Okay? So this is a really big deal as far as its power. Okay? The number itself, meh, probably won't ever use again. Okay? So let's get an idea of a mole of several substances. So if we take a look at the U.S. national debt down along the bottom, we might all agree that that is a really big number and not a good thing. If we look at the scale of a mole, okay, 6.02 times 10 to the 23rd, okay, if we compare that across, our national debt looks like peanuts in comparison. Okay? The mole is massive. Okay? The next thing that becomes kind of confusing is that if we then go through and look at different substances, okay, that picture there, which I believe came from your textbook, shows a mole of a variety of different compounds. Okay? And you'll notice that we're seeing varying amounts of each of those. So, well, but isn't a mole the same? It's the same number. That doesn't mean it's the same volume. That doesn't mean it's the same mass. Okay? Because our size is changing for each of these elements, which means the volume will change. Our mass is changing because we're adding more protons and neutrons. Okay? So everything is changing as far as the mass and volume. The one thing that will remain constant is the number of particles present. Okay? So that's kind of neat. Okay? Other things that we could use to compare, we've got some fun little kind of facts on the side here. There's quite possibly a mole of stars in the universe. So if you wake up, in the middle of the night, go outside and start counting stars, eventually maybe you might be able to account for all the stars in the universe, and that might be a mole. Okay? If we took a mole of our textbook, okay, and then covered it, started stacking them across the U.S., it would cover the entire United States of America to a depth of about 200 miles. Okay? That's how tall this stack would be. That's pretty huge. Okay? 1 mole is approximately the number of milliliters of water in the ocean. Okay? That tiny little milliliter thing, if we used a mole of those milliliters, that's how much water is in the ocean. That's a lot of water. Okay? And then the last one, if we took 1 mole of particles the size of sand grains, so really, really, really tiny sand grains, okay, and then we said the amount of those grains that were released in the eruption of Mount St. Helens, which is probably less relevant for you guys, that would cover the entire state of Washington to the depth of a 10-story building. Okay, so roughly 100 feet. maybe 120 feet. Okay? That's a lot of sand. Okay? So a mole is a huge, astronomically, literally, large value. Okay? So what could we do with this? We could play around with some more conversions. If we take 6.022 times 10 to the 23rd pennies, and we gave this out to every single human on the planet, man, woman, and child, and don't quote me on the numbers that were getting pulled out here, so roughly 4.9 times 10 to the ninth humans, okay? And every human, if we make the assumption that every human lives for 100 years, then how many dollars per hour, mind you, would each human need to spend? Okay, this is a complex conversion. Let's go ahead and see if you guys can come up with it in the quiz that's going to pop up now. And for those of you coming back, hopefully what you got for a number, assuming I did the calculation right, because I could have just as easily messed it up, is that you would need to spend roughly $14 million per hour. Every human, every single one, per hour. That's a lot of money. Okay? That would have covered all of the pennies, okay, in a mole. Big, 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 big number. Okay? So just as a big refresher behind all of this, okay, a mole is a really big number. Okay? And that on its own is pretty irrelevant. Okay? So we aren't concerned about that. But what we are concerned about is that it is a conversion factor. Okay? And more importantly, that conversion factor scales our chemistry up to a measurable value. Okay? So the term becomes a massive part of chemistry vernacular. Okay, but the value is rarely, if ever, used again. But if you ask any chemist, they'll be able to regurgitate 6.022 times 10 to the 23rd as the measurement for a mole, because it's just so beaten into our heads. Okay? But that value is kind of not used once we get beyond this kind of, okay, let's just scale that up. Okay? So the big deal out of a mole is that the periodic table gives us a conversion factor, and that conversion factor is our molar mass. That is our grams per mole. That is a huge piece of information. Okay. The next part will be real quick, conversion factors and where to find them. You are going to be responsible for a lot of conversion factors in this next unit. Okay. We talked about measurements. Okay. There's tables of them in your textbook or online or even in your calculator. The metric conversions must be memorized. You're required to know those. The English conversions will be provided on the exam or in your textbook if you're doing homework. If we're trying to convert between the number of different atoms, okay, well, we can do that when we look at the subscripts in our formula. Okay, that said, our formula must be correct. Okay, I can't look at the number of atoms in sodium sulfate if I think the formula is just Na, whoops, come on, okay, is just NaSO4. Okay, well now when I say the number of atoms, that doesn't make sense. There's one atom in sodium sulfate, one atom of sodium. Well, no, you didn't balance the formula. The formula must be correct. So you have to be good at your nomenclature. If your nomenclature is weak, you're going to start screwing this up too. Okay? So our subscripts give us that information. We can figure out the number of molecules. We can get that from the coefficients of a balanced equation. Okay? So for instance, for the equation below, I know I need to react 2 iron plus 3 ions with 1 tin plus 2 ion, and then that will get me these products. Okay? So I have a conversion factor there. The next one is our numbers of moles. Okay, this is kind of a big one. This goes right back into our number of molecules and the number of atoms. Okay, because molecules and atoms are a unit. Okay, so we can just use or get our number of moles from the formulas, just like we got our number of atoms. We can get our number of moles from equations, just like we got our number of molecules. Okay, and that's really what Avogadro's number is doing for us. It allows us to choose which unit we want to work with. Okay. The last thing to worry about is our atomic mass is to molar mass as grams per, or sorry, whoa, that should not say grams, that's a massive typo. that should say AMUs per atom, is 2 grams per mole. Okay? That information is found on the periodic table. Okay? That is our number of where we would classify our atomic mass. Okay? So you need to be able to find these and manipulate them. Well, how do you manipulate them? We need to be sure we're using our units, which is what we talked about in that last unit. We have to have our measurement and the substance. Okay? You need to then be able to find the conversion factors, which involves going to your textbook, going to the exam, or using your brain because you've memorized it. Okay? You need to be able to manipulate those in some organized fashion. One method that we use for that conversion is called dimensional analysis, or the unit factor method is what your textbook calls it, but it's dimensional analysis. So what we've got is an example conversion along the bottom there of how we could potentially convert in between each of those units and where that conversion factor is found. Okay? A large part of this unit is going to be tracking conversion factors and making sure you manipulate and use them correctly. It takes time and practice, so start now.